Okay, guys. So we're going to start talking about acids and bases. So we'll talk about kind of basics of acids and bases, and we've already talked about them a little bit when we were talking about reactions, but we'll go in a little more depth about the behavior of acids and bases in a little different way we can look at um, how they're behaving as opposed to just the general type of acid and base reactions that we looked at back in chapter 5. Um, so let's see. First, let's start with just general characteristics of acids and bases. So most of the time, you're kind of familiar with this stuff maybe. And so there's different characteristics substances have typically if they are acids or bases. One thing you could talk about the taste. Now, of course, when we go in the lab, we're not tasting things, but just everyday chemicals actually can be acids and bases. And that, or they can contain an acid or base, and that can affect then the taste. So things that tend to have a sour taste typically are acids or they're acidic in some way, whereas things that are more bitter tend to be bases. Um, Also, base solutions, so liquids that are bases tend to be kind of slippery. So like soaps and stuff tend to be basic. Um, and then acids can actually dissolve metals. It kind of depends on what the acid is and if the metal, has a coating on it that can protect it or not. But they can cause metals to corrode. And then we can do tests in the lab. So things like use litmus paper. And so general litmus paper, red or blue, is used to test for acids or bases. So if you have blue litmus paper and you put it in a solution, if it turns red, that solution is acidic. If you have red litmus paper and you put it in a solution, if it turns blue, it's basic. There's also more, fancier type of litmus paper. You can have actual pH paper that changes different colors for different pHs. And then there's other types of indicators, things that you could add to a solution that would change to a certain color depending on if something is acidic or basic, or above or below a certain pH. That's something you'll look at in next week's lab. You'll look at actual pH and different indicators. And let's see, the last thing, when we have acids and bases, those things react with one another. So they neutralize one another, okay? Meaning that they react with what is making something an acid or base, okay? So they take away that property and neutralize it. And then if you want to look at the numbers, we can talk about a pH value. We will look at this a little bit more on Tuesday because we will actually do some calculations of pH. Maybe at the end of today, we'll start talking about that. Just depends on how far we get. But you should in general know that acids have a pH value of less than 7, whereas bases have a pH value greater than 7. Usually, here we go. Anyway, usually it's on the scale of 0 to 14, but realize the pH scale can go kind of outside of those limits a little bit. Also, pH of 7 would then be something that is considered to be neutral. Okay, so we'll talk about the actual numeric values a little bit later. But first, we want to go through looking at these actual substances and being able to look at a substance and kind of have a general idea of is it an acid or base, and what's going to happen when this is put in solution, and how we can kind of categorize them. So our first way to kind of categorize acids and bases is by using what we call the Arrhenius definition, which, here we go. So you can have an Arrhenius acid or an Arrhenius base, okay? Or you can have something that isn't even one of those things. But if you have a substance and it's classified as an Arrhenius acid, then that is something that ionizes when it's put in water and it produces H plus, okay? So when we say something ionizes, that means that you started with this substance, whatever it is, and it splits apart into ions, okay? And so it's going to split apart and it's going to at least give up an H plus, maybe multiple, and then what's going to be remaining is some anion, okay? So an example, as I have given there, is HCl, okay? So HCl by itself is going to be a substance that's going to be in the gas phase. And so if we took HCl gas, hydrogen chloride gas, and we bubbled it into water, okay, so we pump the gas and bubble it through some water, what's going to happen is some of it would dissolve, okay? And when it dissolves, it actually ionizes and splits up into H plus and Cl minus. So since that is something that ionizes in water to produce H plus, then it's an Arrhenius acid, okay? Whereas an Arrhenius base is something that ionizes in water to produce OH minus, okay? So you have this neutral substance, you put it in water, and what happens is it splits up into ions, and one of the ions is OH minus, okay? Meaning the other one's got to be some cation, okay? So you can have different acids and bases because that other piece of the compound can be, you know, some other ion, any other ion, okay? I guess I shouldn't say any other ion, but there are, you know, other anions or cations they could be. So for the base, I gave you the example of sodium hydroxide. So sodium hydroxide by itself is just a solid. It's just like an ionic compound, okay? But if you put that in water, it's going to dissolve. And when it dissolves, it splits up into Na plus and OH minus. So since it gives you OH minus, it is a base, okay? The Na plus part is just an extra piece. It's there because you can't just have OH minus, okay? So you have to have something to balance the charge. Same with the HCl. It gives you H plus when you put it in water, so it's acting as an acid, and then it leaves behind then that Cl minus, okay? But you can have lots of other acids. What's going to be different is it's going to leave some other anion, okay? Whereas you can have other bases, it'll just have different cations, okay? But for an acid, you always have H plus produced. A base, you always have OH minus produced, okay? And that's how the Arrhenius definition looks at it. Now, a couple other things for the acids, they can be what we call monoprotic. That's what HCl would be. What that means is it releases one proton for every one molecule. Okay, so for one HCl, it gives you one H plus. So that's monoprotic. It can also be diprotic, meaning it would give up two protons. So that would be something like, if you want to talk about a diprotic acid, you would have something like H2SO4, okay? Whereas a monoprotic would be something like HCl, okay? So H2SO4 has two protons it could give up. And when I use that term proton, I'm talking about H plus, okay? That's interchangeable. We can call it hydrogen ion, or we can call it a proton, because when a hydrogen atom loses its electron, forming the positive charge, all that remains really is a proton, okay? So H2SO4 would be a type of diprotic acid, or you can have some sort of polyprotic. Polyprotic is kind of more of a generic term. That means you have more than one proton. So H2SO4 could also be considered polyprotic, or something like H3PO4, so phosphoric acid. That's a polyprotic acid because it gives you multiple protons. In that case, it would give you 3 H pluses, you know, for every one, or at most that's what it could release in solution, okay? Now with this, one other thing that it's good to know is that even though, you know, I wrote that first reaction, HCl going to H plus and Cl minus, a lot of times, instead of writing H plus, we'll write H3O plus. And so I could write the reaction instead as HCl plus H2O Okay, so show it actually interacting with that H2O and say that it forms H3O plus and Cl minus. So what happens is when that acid releases H plus, it doesn't stay H plus. It actually is attracted to the negative end of a water molecule. So it's in a solution of water, and what happens is that positive charge goes and kind of sticks to a water molecule. And so it forms what we call a hydronium ion. Okay, and your book talks a little more about it. It actually can cluster even larger, but we'll just talk about it in terms of it associating with one water molecule. Okay, so sometimes you'll see reactions where people write it as H plus, and sometimes people will write it as H3O plus. Both of those, are just an indication that a substance gave up an H plus. Okay, let's see. For your bases, we can use kind of another kind of system of generic terminology. So for acids, we say monoprotic, diprotic, polyprotic, just to say how many H pluses it's giving. We can do the same with bases. So we can call a base, we can say that it's monobasic, or it's dibasic, or it's polybasic. And that tells you how many hydroxides it is releasing in water. Okay, so if it's monobasic, it'd be something like my example, the NaOH. So for every one NaOH, one OH minus comes off. Okay, whereas if I instead had, say, calcium hydroxide, for every one calcium hydroxide, you have two OHs. Okay, and so it's dibasic. Okay, whereas polybasic would be, anything that has more than one. So you could call calcium hydroxide also polybasic. Or we could have something like, say, aluminum hydroxide. That would be AlOH3. Okay, and so that would also be polybasic because you have multiple OH minuses that could be released in solution. Okay, so you should be familiar with that terminology. Now, when we are dealing with things that are Arrhenius acids or Arrhenius bases, those things can react with one another, just like any acid or base. But specifically, when we're talking about Arrhenius acids and bases, the reactions are they always follow a specific pattern, and that's the pattern we looked at in chapter 5. So basically, your acid gives up H plus, your base gives up OH minus, so it's going to form water as one of the products, okay? And then the other product is just a combination of the remaining cation and anion, okay? So your acid gives up H plus and there's still an anion there, and your base gives up OH minus and there's still a cation. And so those cations and anions come together and form an ionic compound, which we generally call a salt. Okay, so when I say the cation and anion come together to form a salt, I'm talking about an ionic compound. Okay, that's just a general term for an ionic compound. Okay, so if you want to see an example, if we had HBr and KOH, so hydrobromic acid, that's an Arrhenius acid, because when we put HBr in water, what you get is H plus and Br minus, okay? And so I can, jot that down. So when you see that, when it's in water, you really have those two ions. And then potassium hydroxide, that's an Arrhenius base, because when you put it in water, you get K plus and OH minus, so it gives you OH minus. And then you should be able to predict products, because like I said, we already kind of looked at this back in chapter 5. And so if you can focus on what are the ions that I get from this Arrhenius acid and Arrhenius base, all you have to do is swap ion partners. Okay, so the H plus goes with the OH minus, okay, and then the K plus goes with the Br minus. Okay, so the H plus and OH minus give you water, and then the K plus and Br minus give you KBr. Okay, so H2O is our water, KBr is our salt. And that salt is going to be dependent on what cation and anion came in with your acid and base. Okay, so that will vary. just like your acid and base can vary, okay? But the water part always gets produced if you have a reaction between an Arrhenius acid and an Arrhenius base, okay? So that's the most common type of acid and base that we work with in this class. But it's not the only kind of acid and base you can have. So that definition, the Arrhenius acid-base definitions, those are kind of limiting, okay? And so it doesn't encompass everything. And so sometimes we will talk about acids and bases a little bit different, okay? And what we use is what's called the Bronsted-Lowry definition, okay? And so the Bronsted-Lowry definition of acids and bases says that an acid is a proton donor. So it's putting it a little bit differently. Instead of saying we have a substance and it produces H+, it's something that donates a proton. So essentially those things are saying the same thing, just a different way, okay? So in terms of an acid, it's not something new, but in terms of a base, it's looking at it from a different perspective, and it sometimes then can encompass more, okay? So the base definition says that a base is a proton acceptor. So instead of being something that produces OH minus, okay, it is something that is picking up H plus, okay? So this can encompass more substances, because in order for something to be an Arrhenius base, something that produces OH minus, it really needs to be something that contains OH minus within it, right? Because if it doesn't have OH minus, how can it release OH minus? It can't. But something can actually act as a base or behave as a base if it is capable of accepting a proton, accepting an H plus, okay? So that's, you know, the Bronsted-Lowry definition. It's focused on, is this substance giving an H plus or is it taking on an H plus? And whatever it's doing with H plus tells you if it's an acid or base, okay? So an example of a Bronsted-Lowry acid would be HCl. We can also classify that, like I had on the last slide, as an Arrhenius acid. Either way, but basically this is the second way I had written the reaction on that first slide. So when HCl interacts with water, what it does is that HCl molecule donates the H plus. So it donates it actually to the water molecule. So what remains of that acid is just Cl minus, and now it's just an ion, okay? And where the H plus went is to the water molecule, forming the H3O plus, okay? Whereas an example of a base would be ammonia, okay? That's a really common Bronsted-Lowry base, is NH3, which is ammonia. Or if you want to use general systematic naming, you could call it nitrogen trihydride. It's just no one really does. We call it ammonia instead. And so that's a substance that can accept a proton. So it naturally will attract H plus to it. So if there's anything around that has an H plus that's willing to give up, or if there's free H plus floating around in the solution, NH3 will pick it up, okay? And so what it forms then is the ammonium ion, NH4 plus, that's the ammonium ion. And that means if that came from a water molecule, like I have written here, then what's left of the water molecule is just OH minus, because it lost an H plus, okay? And that H plus went to the NH4, or to the NH3, forming NH4 plus, okay? So those are general examples of a Bronsted-Lowry acid and a Bronsted-Lowry base. But what you have to realize is in this process, you can't only have one of those things happening, okay? So for an Arrhenius acid, you could have an Arrhenius acid interact with something else and it not be involved with a base, or an Arrhenius base, you know, giving up its hydroxide and it's not actually interacting with an acid. It just wouldn't form a salt and water if it's not an acid-base reaction. In this case, If you have something that is donating a proton, giving up an H plus, there has to be something else there that is accepting it, okay? Or if you have something accepting an H plus, there must be something else there that is giving that up, okay? So these have to go together, whereas the Arrhenius acids and bases can act independently of one another. For Bronsted-Lowry, they cannot. They have to be paired. So that means in these two example reactions that I give, if HCl is an acid, there must be a base there. If it's a Bronsted-Lowry acid, there has to be a Bronsted-Lowry base. And in this case, it would be the water molecule, okay? Same with for the NH3. The water molecule must be acting as an acid to the base of NH3, okay? And that's because it's doing the opposite process. So if HCl is losing that H plus, it's giving it up, it's donating it, whatever is picking it up is acting as a base. So in the first reaction, H2O is acting as a base because it is acting as a proton acceptor. So going from the left side of the reaction, you have H2O, and on the right side, you have H3O plus. So it has picked up a proton. It has accepted a proton. So the H2O is acting as a base. Whereas in the second reaction, the H2O gives an H plus to the NH3, okay? So it goes from being H2O to OH minus, okay? So the H2O in that case, since it's donating H plus, is an acid, okay? And so those are always paired together. If you're looking at Bronsted-Lowry type process where something's giving up an H plus and something's taking on that H plus, you always have an acid and a base in that reaction as reactants. Okay, so that's really important to realize. So if you're given an acid-base reaction, you should be able to determine what substance is acting as an acid and what substance is acting as a base. Okay, so something's donating a proton, something's accepting a proton. Okay, now with this, you need to realize that you can have substances that can act as both an acid and a base, okay? And so in one reaction, they can act as an acid, and in one reaction, they can act as a base. Those things we would call amphoteric. So if I go back a slide for a second, you have water in one reaction is acting as a base, right? And in another reaction, water is acting as an acid. So water is an example of an amphoteric substance because it can behave as an acid in one situation and a base in another, okay? So it depends on what's present. So another example would be hydrogen carbonate ion or the bicarbonate ion. So that's the reactions I have here. I have HCO3 minus acting as an acid and HCO3 minus acting as a base in another reaction, okay? So in the first one, you have HCO3 minus reacting with OH minus. Okay, so it's reacting with something that is a strong base. So this is written in the ionic form. They've dropped the spectator ions, okay? And so what happens is the OH minus is really going to want to pick up an H plus, and the HCO3 minus has an H plus it can give, okay? So if something has hydrogen, it potentially could give up H plus, but there's lots of things that have hydrogen that don't, okay? So you do have to be a little careful. Usually you look at the chemical formula, and if the H is written first, then normally that is an acidic hydrogen. So it's one that can be donated, okay? So since I wrote this as HCO3 minus, writing that H first is kind of a hint that that is capable of being donated. Okay, it doesn't mean it's always going to be donated, but in this case it is, because if you look from the left-hand side to the right-hand side, you have got HCO3 minus, and then it becomes CO3 2 minus, okay? And so it actually is donating that proton. So it lost an H plus and becomes CO3 2 minus. Whereas in the second reaction, they've indicated it acts as a base, and that would mean that it needs to pick up a proton, which it has the capability of doing that because it has a negative charge. Anything that has a negative charge will naturally attract positive things to it. So if there's an H plus around or something that's willing to give one up, it'll take it, okay? And so in this case, then it goes from HCO3 minus to H2CO3, okay? So it picks up an H plus specifically from this hydronium ion that it's reacting with. So since there's hydronium ion in that solution that has an extra H plus, it's willing to give that up. And so since there's something with a negative charge around, it will take it, okay? So in this, we have it acting as an acid and as a base, okay? So that's an amphoteric substance. Anything that can either donate or accept a proton, okay? So if it can do both, okay? In order for something to be able to donate a proton, it needs to have one. So if you have a substance that has no hydrogen, it can't possibly act as an acid, okay? But if it has hydrogen and we've written the formula with the hydrogen first, that probably means it can donate that, okay? We generally wouldn't write it first if it couldn't. And then things can typically accept a proton if they have a negative charge, or things that have lone pairs on highly electronegative atoms. So we'll talk about that a little bit more when we get into bases, okay? But there's another important term or kind of set of important terms that you need to be familiar with. When we're talking about this Bronsted-Lowry type of acid-base behavior, what we have is conjugate acid-base pairs, okay? And so you actually always, in a Bronsted-Lowry reaction, have two conjugate acid-base pairs, okay? And these are substances that are related by a transfer of a proton, meaning that they're one proton different or one H plus different. So remember, anytime we use that word proton, we mean H plus, okay? So if we call something a conjugate acid, that's a substance that was a base and it has an extra H plus on it now, okay? Whereas if we call it a conjugate base, it's the acid that now has one less proton, okay? So I have an example down at the bottom here. We have HCl as an acid, and if we say that's an acid, that's something that's giving up an H plus, right? And when that gives up H plus, it forms Cl minus. And so Cl minus is the conjugate base of the acid HCl, okay? Because they differ by an H plus, okay? And the thing with the H plus is the acid, and the thing that is missing that H plus is its conjugate base, okay? Whereas then I have labeled in this reaction H2O is the base and H3O plus is the conjugate acid, because what happens is that H2O picks up an H plus, okay? So the H2O is the original substance, and since it's picking up an H plus, it's acting as a base, and the thing that now has that extra H plus is called the conjugate acid, because now that substance could actually donate the proton. Okay, we can also look at those reactions above. So if in the first reaction, if HCO3 minus is an acid, then the CO3 2 minus must be the conjugate base, okay? Because that is the substance that is now lacking that proton, okay? So they differ by an H plus. The thing that is short in H plus is the conjugate base, okay? Whereas in this reaction, the OH minus is actually my base, because that's the thing that's accepting protons, and the thing that it's related to is the water, and so that water that now has the extra proton is the conjugate acid, okay? And then in the second reaction, the HCO3 minus is acting as a base because it's picking up a proton, So what gets formed, what actually has that extra proton is its conjugate acid, okay? And then if the HCO3 minus is the base, the H3O plus must be the acid. And when that donates the proton, what remains is the H2O. So that's the conjugate base, okay? And so in these reactions, there's always two conjugate acid base pairs. And so in this first reaction, this is our acid, right? And this is our conjugate base. And so this is one conjugate acid base pair. And then OH minus is our base and H2O is our conjugate acid. So that's our second conjugate acid base pair, okay? And then in this second reaction here, you have the base and its conjugate acid, and then the acid and its conjugate base. Those are conjugate acid base pairs, that set of two compounds. And the difference between them is always one of them has an extra H plus or one of them's missing an H plus, okay? And your reactants are always what we call the acid or the base. And the products are what we call the conjugates, okay? So you've got to be familiar with this terminology. You should be able to identify these given a reaction, okay? You should also be able to determine if we just give you a substance and say, okay, the substance, if it acts as an acid, what's its conjugate base? Or if this substance acts as a base, what's its conjugate acid? Okay, so you should be able to interconvert between those. So let's look at an example. If we have HPO4 2 minus, which is hydrogen phosphate ion, and I tell you that's an amphoteric substance, meaning that is something that is capable of acting as an acid or as a base, okay? So it can act as both, and how it's going to behave depends on what it is with, okay? So it can react with lots of substances. But one way that's really easy to deal with this is to think about what can happen if it reacts with water, because we also know water is amphoteric, so water can go both ways. And so if I want to know what's the conjugate acid of this substance and also what's the conjugate base, then I need to think about what happens when this reacts as an acid and what happens when it reacts as a base. So let's look at if you have HPO4 2 minus, we have that, and let's say we react it with water, okay? If we first want to act like that's an acid, okay, if that behaves as an acid, it needs to donate its proton to water. And if it does that, then what's going to be left of it is PO4 3 minus, right? Because if it donates its proton to water, and then the water is going to become H3O plus, okay? So in this case, if this is the acid, then this is the conjugate base, because that's what remains when that substance donates its proton, okay? And so PO4 3 minus is one of my answers. That's the conjugate base. And then if I think about it the other way, where I have HPO4 2 minus, and let's again just react it with water. That's usually the easiest way to think about things, because water can do both. And so let's say that now this substance is going to act as a base. If it acts as a base, that means it needs to accept a proton. So it needs to pick up an H plus, and water can give that H plus. So if it picks up an H plus, it becomes H2, because now I have two H's, and then still PO4, but then my charge changes as well, right? Because I'm picking up an H plus, and so it becomes just a -1. Whereas in the other one, when I gave up the H plus, now I don't have the H at the end, and my charge went down because I lost a positive, so it becomes more negative. Okay, and then the water gave up that H plus, so what's left of the water is OH minus, okay? So in this case, if my HPO4 2 minus is the base, that means that my H2PO4 minus is my conjugate acid, okay? And so that one, let's see, where is it? It's here, okay? That must be my conjugate acid then. Okay, so that's an amphoteric substance because it can donate a proton and it can accept a proton, okay? And you should be able to identify what are the conjugates of this, okay? Now, let's see, let's look at one more example here. So I give you a list of different pairs of substances, and I want to know which of these are not a conjugate acid-base pair, or are they all conjugate acid-base pairs? So what you need to realize is a conjugate acid-base pair has to differ by an H plus, right? And so if we look at, you know, like SO4 2 minus and HSO4 minus, well, SO4 2 minus, if we added an H plus, then we would get HSO4 minus, right? Because we'd have that additional H and our charge would increase by 1, right? So that is a conjugate acid-base pair, okay? Then we have HC2H3O2 and C2H3O2 minus. And so that substance, if you took that and took away a proton, okay, you would get C2H3O2 minus. And so that plus H plus, right? So you take that anion, add H plus, you would get that neutral substance, right? So those also differ by an H plus, okay? So that is a conjugate acid-base pair. But then we have this HO minus, which usually we write OH minus. I don't know, I just typed that backwards, kind of. And then H3O plus. So if we think about how those two relate, well, if I added H plus to OH minus, would I get H3O plus? And the answer is no, okay? Those aren't related by an H plus. The only way those would be related is if I added 2 H pluses to OH minus. So that is not a conjugate acid-base pair, okay? So that is actually what we're looking for, what is not. So that would be, you know, an answer. Now let's check and make sure this last one isn't another one. So we have H2SO3 and HSO3 minus. So if I take H2SO3, I could convert H2SO3 to HSO3 minus if I took away an H plus, or I can go backwards and say HSO3 minus plus an H plus would give me H2SO3. So those are linked by an H plus, okay? So that one is a conjugate acid-base pair, so that's not what I'm looking for. And they're not all conjugate acid-base pairs because we've determined that OH minus and H3O plus is not a conjugate acid-base pair. So they need to differ by 1 proton, okay? So based on kind of the way I wrote these, looking at the connections, in this first case, the SO4 2 minus is acting as a base, and the HSO4 would be my conjugate acid, okay? And then my HC2H3O2, that would be acting as an acid and forming its conjugate base when it loses its H plus, okay? And then the H2SO3 would be acting as an acid, and it would form its conjugate base of HSO3 minus, okay, if you want to classify how they relate to one another, okay? Okay, now, let's see. Let's talk a little more in depth about how an acid and base behaves in solution, okay? Because there's 2 kind of classifications. We can have strong acids and bases, and we can have weak acids and bases. And how they behave in solution is different, and it's important to know the difference and know why we would call something a strong acid or base or a weak acid or base, okay? So it's telling us something about how it behaves in solution. And so, as I have indicated here, your strong acids and bases are actually strong electrolytes, okay? Meaning they completely ionize. So they completely break up into ions. So even though we put usually this neutral substance in solution, okay, it could be something that we put in that was already ions. So we're kind of putting this ion in solution and then it further splits. But essentially we're taking this substance, we're putting it in solution and it splits up completely into ions. That would be the behavior that you'll see with strong acids and strong bases, okay? And so I give you a little bit of indication here of what types of substances fall into these categories. So strong acids, we do typically kind of limit it down to these 7 that I have listed here, okay? Sometimes people draw the line at a little different place, but pretty much the things that split apart completely acting as acids in solution are going to be limited to HCl, HBr, HI, HNO3, HClO4, HClO3, and H2SO4, as you can see there, okay? So those you just generally are expected to know, okay? Now your book gives you a table of them. You can look up in the table, but you need to be aware there is just this short list of substances that act as strong acids, and anything else you identify as an acid would be weak, okay? Whereas strong bases, the most common type of strong bases are going to be hydroxides, and specifically hydroxides of group 1 and group 2 elements, okay? So hydroxides are compounds that contain OH minus, which is hydroxide, right? And group 1 and group 2, most of those are strong bases, not all of them. You do have to be careful. I have a table on the next slide, which is what's given in your book, and I'll add to it a little bit for you. But you should know those general, indications of what type of things you should recognize as strong acids or strong bases. Now, if we look at how they behave in solution, it's kind of what we've already been looking at, or similar to what we've already been looking at. So if we have HCl, this is, our example, this is our most common one, but you can write a similar reaction for any of them. So you have your strong acid, so in this case, HCl, and when it's added to water, what happens is it completely splits apart. And so it gives you a bunch of Cl minus and a bunch of H plus, and those H pluses each bind to water molecules. Okay, so your products then are H3O plus and Cl minus. So pretty much you put it in solution and all you're going to have in the end is ions. You don't have any HCl left. Okay, it's all broke apart. That's the key for it to be a strong acid. Whereas for strong bases, you put this in water and it also completely ionizes. So we put something like NaOH because that's a group 1 hydroxide. Sodium is in group 1 of the periodic table and it is bound to hydroxide, OH minus. Okay, so once we put that in water, it actually splits completely into Na plus and OH minus. Okay, and so that's all we should have left. We shouldn't have any NaOH, okay? And that is what happens with any strong base, okay? So any strong acid, any strong base should completely split up into ions. And so they're classified as strong electrolytes because they produce a bunch of ions in solution. And if there's a bunch of ions in solution, then it can conduct electricity very well, okay? So like I said, your book gives you some tables. So a lot of times people would assume these things are strong acids and strong bases. You guys can always look in the table. You need to at least be aware there's a table I can look at to determine is this a strong acid or strong base, okay? But I do want to point out, so in the first table, they do give you the 7 that I gave you. Those are the ones that you should be familiar with or be able to look up in this table and know that they're strong. But on the table of common strong bases, they leave out a couple of important ones. And so You really should also add on that rubidium hydroxide is also a strong base, and cesium hydroxide. Okay, and so those two are also group 1 hydroxides. So group 1 of the periodic table has lithium, sodium, potassium, rubidium, and cesium. Okay, and all of those things, you put them in water, they break apart completely into ions. I guess they put only lithium, sodium, and potassium in the table because those are the most common for us to deal with. But the rubidium hydroxide and cesium hydroxide are common enough. It in general is expected you know those as well. But then they give you magnesium, calcium, and barium hydroxide on the right as strong bases. Now, I'll caution you here. They list magnesium hydroxide. That one is a little iffy. A lot of times we wouldn't call that a strong base, but since they put it in the table, we'll go with it. One that they do leave off that we do consider a strong base is strontium hydroxide. Okay, so usually I would say it's the group 1 metals and the heavy group 2s. So calcium, strontium, and barium are lower on the periodic table. They're the heavier elements. When those things are bound to hydroxide, they tend to completely break apart, meaning they act as a strong base. Magnesium hydroxide isn't very strong, okay, but since it's in the table, we can kind of treat it that way for now. Okay, but let's talk about now what's the difference if then we call something a weak acid or a weak base, okay? So this does change things a little bit. If it is a weak acid or weak base, then it is a weak electrolyte, meaning it's something that only partially ionizes, okay? Meaning it's actually going to exist in equilibrium with the ions. So you're going to have some of the neutral compound that you initially put into the solution, but you're also going to have some of it broke apart into ions, okay? You actually end up having way more of just the neutral compound dissolved, okay? So you only get a small amount of ions for these, okay? And just like with the strong acids, I give you kind of an indication of some substances that are weak acids and weak bases. So for weak acids, I just list a few common examples. So hydrofluoric, acetic acid, and nitrous acid. Those are some common acids that we deal with that are weak acids. Really, the way you know if something is a weak acid is if it's not one of the 7 strong, okay? So key is determine if you have an acid, is it one of the 7 strong? And if it's not one of those 7 that we call strong, you assume it's weak, okay? Because it's weak, okay? But for the weak bases, that is a little different. These are the substances that you might not immediately realize are a base, because usually the bases that we deal with are hydroxides, okay? But in this case, our weak bases, it could be the hydroxides of other elements that we didn't talk about on the previous slide. But a lot of times weak bases we deal with actually are something where there's a hydrogen attached, where there's a lone pair attached to a highly electronegative atom. And that's because then that lone pair that's on a highly electronegative atom will strongly attract H+ to it, meaning it behaves as a base, okay? And so when we deal with these, it's usually you have some sort of organic compound that contains nitrogen or oxygen, okay? Because when you have nitrogen in an organic compound, so nitrogen attached to some carbons, or just nitrogen with hydrogen, then it has a lone pair on it. And that lone pair, that negative charge, is going to naturally attract H+ to it. Same with the oxygens. When oxygen's in an organic compound, so it's attached to some carbon, it always is going to have 2 lone pairs on it. And so it's got this negative charge on it that it will pull H+ towards it, okay? And so an example of the behavior of a weak acid, if we focus on hydrofluoric acid, so HF, when we put that in water, it does ionize partially. And so it forms some F minus and some H plus, and that H plus, attaches to water, so it forms hydronium ion, okay? But it only partially does that. So within the solution, we actually have lots of HF, and then we have some H3O plus and F minus, okay, in a weak acid solution. But if we had a strong acid solution, remember, it completely breaks apart. So that's the big difference, is does it break apart completely or just partially? Same with your weak bases. A good example is ammonia. So if we put ammonia in water, when it picks up a proton, it only partially does that. So some of the NH3 molecules in that solution will take a proton from a water molecule, but a lot of them are still just NH3, okay? And so how that is indicated when we write a reaction is by using the equilibrium arrow, okay? So remember, we were talking about equilibrium last time. So equilibrium reactions, and so how you have some reactions that occur in the forward direction only, and you have some that occur in the forward and the reverse, okay? And when they occur in the forward and reverse direction, those reach equilibrium, okay? So a point where the forward and the reverse are happening at the same rate. So this always occurs when you have a solution of a weak acid or weak base. When you initially put it in, it starts to ionize, but eventually enough ions build up that those ions will start reproducing the neutral substance, and then it'll just both be happening, at the same rate, okay? Whereas for a strong acid or strong base, you put it in solution and it just breaks apart completely. So it only goes in the forward direction, okay? So the ions don't come back together, okay? Unless if you were to take the water away, which we're not talking about that, okay? So your book also gives you some tables of common weak acids, common weak bases. This I find to be a little less useful because you could have an unending list, or what feels like an unending list of weak acids and weak bases, okay? They just give you some common examples. The lists of strong acids and strong bases are going to be much more useful because there is an end, a definite end to those lists, okay? And so at least reference the strong acid, strong base tables. But this is nice to just get an example. And a lot of the everyday stuff we deal with that are acids and bases are actually, they're weak acids and weak bases. Otherwise, they wouldn't be something we dealt with daily, because strong acids and strong bases can be very dangerous, okay? You can get injured if you get a lot of strong acid, strong base on you, or even a little. And so our everyday substances, the things we're working with regularly or eating, consuming, utilizing in your household, those are weak acids and weak bases. So things like vinegar or soda or different fruits and vegetables, maybe not vegetables, mainly fruits. And then like different soaps and cleaners and stuff. Those things are acids and bases, but they're weak, okay? So meaning they do have the capability to either produce H plus or pick up H plus from things, but they only partially do that, okay? So not to an extent where it can harm you, okay? Or at least as long as you're not exposed to too much, I guess, potentially. Now, let's talk about how we would quantify kind of the strength of acids, or even the strength of bases, we could say, but we're going to focus on the strength of acids, okay? And really how we quantify the strength or determine whether or not something is strong acid or weak acid is how much it dissociates, right? How much it ionizes, how much things break apart, okay? So if we want to actually quantify how strong this is, so if we have a bunch of weak acids, instead of saying these are all weak, we can actually rank them, and say, even though these are weak acids, this one's really strong compared to this one, okay? And how you determine that is by kind of measuring how much of this, what portion of molecules actually ionize. And the more that ionize, the more that split apart, the more H plus you have, meaning the stronger its acid behavior is, okay? So we can actually quantify this by looking at the equilibrium reaction and writing an equilibrium constant expression for the acid behavior, okay? And so you're going to have an equilibrium constant associated with the behavior of any weak acid or even weak base, okay? So in this case, if we're talking about acids, then we would kind of quantify how strong it is based on the acid ionization constant. And so that is the Ka value, okay? So it's the same thing, or it's the same general idea as an equilibrium constant, okay? So a K or KEQ. But this, it's just labeled as a Ka because specifically it relates to an ionization of an acid. So it's always some acid molecule reacting with water, forming H3O plus, and then leaving behind the anion, okay? So I give you a general form of the ionization of a weak acid here. So in this reaction given, this HA molecule, that's my weak acid. That can be representing any weak acid. So say I have HF. HF is a weak acid. And so how that ionizes is it reacts with water, right? And then it forms H3O plus because it donates a proton. And then what's left behind is the F minus, okay? And so that's what's kind of represented in this reaction. The HA is my HF, okay? And the A minus is the F minus, okay? But it could be, you know, some other weak acid as well. It doesn't have to be as simple as HF. Say we have acetic acid. We could write a similar reaction. You could have HC2, H3O2, right? That's acetic acid. So that's something capable of donating a proton. That could interact with water, and it would reach an equilibrium because it's a weak acid. So it would donate a proton to water, forming hydronium ion. And what would be left behind is what remains. So C2H3O2 minus, okay, would be our A minus in this case, okay? So realize that this reaction down here, that's a generic form showing you the general form of any weak acid ionizing in water, okay? So the HA is whatever acid you're talking about. H2O is always H2O, and the H2O always is picking up that proton, so it's becoming H3O plus. And then A minus is just whatever anion is left behind by that acid, okay? And so you should be able to write this equilibrium associated with any weak acid given, but then how we kind of quantify how weak it is or how strong it is based on that Ka value, okay? And the Ka value, you can either calculate if you were given the information, or you could look it up in a table. Usually you find tables of them. But realize that just like any other equilibrium constant, they relate to the equilibrium expression. And so remember that our K equals equation, that K expression, is always the products over the reactants, okay? The product concentrations over the reactant concentrations raised to their stoichiometric coefficients. In this case, an acid ionization reaction always has coefficients of 1. It's always one of the acid molecule reacts with one water, forming one hydronium and one of the anion, okay? So you actually won't have any exponents in this case, okay? And the other thing is notice that H2O is not in that Ka expression because remember, we leave out pure liquids and pure solids. And H2O with an L after it, that's a pure liquid. So that gets dropped out of the expression. So we just have H3O plus concentration times whatever anion over that weak acid concentration, okay? So that's where those Ka values come from, is by, making these weak acid solutions and quantifying how much of those substances are in the solution and plugging it into here, and you get those Ka values, okay? Luckily for you, you usually would just look up those Ka values, okay? And once you have the Ka value, it gives you a sense of how strong of an acid this is. And how is because what you have to realize is for something to behave as an acid, it needs to donate H plus, right? And so you can get a sense of how strong it is based on how much H3O plus is formed, or even how much A minus is formed, okay? The more H3O plus you have in solution, or the more of that anion that's there, means more H plus is released, the stronger the acid, okay? And so that means that if you have more of this stuff on the top of the equation, you have a stronger acid. So if you have more stuff on top, the Ka value is going to be larger. So, oh, whoops, sorry guys. There we go. A higher Ka value always relates to a stronger acid, okay? That means it ionizes more, right? Because a strong acid ionizes completely, right? And weak acids only partially ionize. But depending on what the actual substance is, which acid will determine how much it ionizes. So some acids ionize more than others. And if it ionizes more, it actually is a stronger acid, okay? And you can quantify that by looking at the actual Ka values, okay? So a higher Ka means a stronger acid, a weaker or a lower Ka means a weaker acid, okay? So for example, here's two values you can look up in your book. So we have acetic acid and we have hydrocyanic acid, and I show you first off the equilibrium of each of those in water, but then their Ka values next to them. And so if you look at those Ka values, you'll see that the first one that's for acetic acid, now notice I'm calling this acetic acid here, and also this up here, acetic acid. Those are the same compound. They're just written in a different order. I apologize, that's common. It depends on who wrote it, on which way they write it. It's the same compound. But if you look at the Ka values, what you'll see is this first one is times 10 to the negative fifth. The second is times 10 to the negative 10th. And a value times 10 to the negative fifth is actually larger. So since this is a larger value, it is a stronger acid, okay? Whereas the smaller Ka means it's a weaker acid. So you can look at the magnitude of those Ka values and it can tell you a ranking of what's a stronger and weaker acid, okay? So you should know what those Ka values are telling you. You should be able to write a Ka expression for something, as well as writing the equilibrium reaction. Of course, you need the equilibrium reaction to write the Ka expression, okay? So like for those reactions I wrote at the top, you should be able to write the Ka expressions for those as well. So not only you should know if I put HF in water, what that produces, right? What's the equilibrium products there, but you should know that for this reaction, your Ka expression is going to be your products. So in this case, H3O plus times HF concentration, or no, not HF, sorry, I guess I should actually be paying attention to the reaction, right? So we have F minus over HF concentration. And so that would be my equilibrium expression for that, or my equilibrium constant expression for that particular reaction. And you can do the same for that second one. So this is kind of combining what we were talking about at the end of chapter 12, equilibrium, with a specific type of equilibrium reaction. Okay, so we talked about it in general, and a common place where you run into equilibrium reactions is with the behavior of weak acids and weak bases. So weak bases do the same type of thing. So if you put a weak base in solution, it reaches equilibrium with its conjugate acid and hydroxide, okay? Those would also have an equilibrium constant associated with them. We won't go into it any further, but what it would be labeled as, instead of a Ka, it would be labeled as a Kb, and it would be called a base ionization constant, okay? So it's, you know, a similar kind of thought process, how to get to those. And the Kb values would also indicate how strong of a base you have. And it's the same type of thing. If it was a higher Kb value, it would indicate a stronger base, okay? But we're focused on kind of the acid part of this, but realize you have all the same comparable type of information to talk about base strength as well, okay? Now, we've been talking about acids and bases, you know, and strong acids, strong bases, weak acids, weak bases. But let's get back to this term of conjugates, okay? So remember that when we're talking about something behaving as, you know, Bronsted-Lowry acid and base, when you have those things reacting, you always form a set of conjugates, okay? And the conjugate of something actually is acting in the opposite way, right? And so if you have something as acting as an acid in the forward reaction, then it forms a conjugate base, meaning that when that reaction goes in the reverse, it actually is acting as a base instead of an acid. Okay, so we have an acid and its conjugate base as a product. And then when that reaction reverses, that conjugate base now is acting as a base and reforming that acid as its conjugate, okay? And the strength of these things are related, okay? Now, the only time you have these equilibrium type processes is when they are weak substances, okay? So no matter which direction you're talking about, it's always a weak acid or a weak base. But their strength has kind of an inverse relationship. So if you have some acid forming a conjugate base in this reaction, the stronger it is an acid, so the more likely it is to release H+, the weaker its conjugate base is at re-picking up that H+, okay? So that equilibrium is going to favor either the acid going in one direction or the base going in the other direction, okay? And whichever one's favored is kind of the stronger one, okay? So usually you would use this information to kind of compare a set of conjugates when you know something about the regular substances. So if you have a set of acids, you have two different acids, and you know, like on the previous slide, we had acetic acid and we had hydrocyanic, right? And I said based on the Ka values, the acetic acid is stronger, right? Because it has a higher Ka value. So I can rewrite those acids real quick. We had acetic acid, and I'm going to write it the more condensed way. So HC2, H3O2, and then we had hydrocyanic acid, right? And this one was stronger, right? And that's because it has a higher Ka, right? And so if we wanted to talk about their conjugates, then the conjugate of this one is C2H3O2 minus. It's acetate ion, right? Whereas the conjugate of HCN is CN minus. That's when it loses an H plus. And so both of those things are actually bases. They're conjugate bases of those particular acids, and the strength of them is going to be reverse of what the acids is. So if acetic acid is the stronger acid, right? This is a stronger acid, then the CN minus, the cyanide ion, is going to be the stronger, that might not be the best writing over that, the stronger base, okay? Whereas this is going to be the weaker base of the two, okay? And so this is the weaker acid. Okay, so their conjugate relationship is opposite of the regular relationship. Okay, so if you have a stronger acid, you know, a strong acid, I shouldn't say strong, stronger and weaker, weak acid, then their conjugate bases are going to have the opposite relationship. Okay, so it's important to realize the same would happen if you have a set of bases. Okay, so if we have two different weak bases and you determine one of them is stronger than the other, then its conjugate acid is going to be weaker. Okay, so the relationship of the conjugates is always reversed. Okay, so if something has a higher Ka value, it's a stronger acid, then its conjugate is actually going to be a weaker base. Whereas if something has a higher Kb value, which indicates base strength, then if you have a higher Kb, it would be a stronger base, meaning its conjugate acid is actually going to be weaker than things that have a lower Kb. Okay? Okay, now let's look at kind of pictorial representation of acid behavior. Okay, so we've got three different diagrams here, acid 1, 2, and 3. And what we're showing here is kind of these different circles. You've got the white ones and the red ones. The white is representing hydrogen, whereas the red is representing the anion of the acid, whatever it is, okay? And so in these pictures, what you should notice is in some of them they're attached and some of them they're split apart, or there's different numbers of them, right? And so in this first diagram, we've got two of them attached, right? And then two of them split apart. So that's indicating about 50% of them are ionizing in solution, right? Whereas in the second one, we have three of them that are still attached and only one of them fell apart. So we've only got 1 out of 4 that ionized, okay? Whereas in the third acid, we only have 1 that's still put together and 3 of them came apart, okay? And so more of them ionized in that case. So we want to know which of the following has the largest Ka. So what you need to remember is Ka is kind of a measure of how much stuff ionizes. Okay, so if you have more stuff that ionizes, you're going to have a larger Ka, okay, or a stronger acid, which in this case, acid 3 has the most ionized, so that must be the strongest acid, okay? Whereas in this case, acid 2 must be the weakest, and that's because it has the least stuff ionized, okay? And so that's your acid strength. But then if you want to think about conjugates, and so each of these things, just the individual red circle, that's our conjugate base. And so in this case, this would have the strongest conjugate base out of these three, and this one would have the weakest conjugate base, okay, out of those. So you got to remember that those relationships are inverse when you are then comparing the conjugates. Now, that gets us through the most of the basics of kind of general acid-base behavior. Next time, we'll talk a little bit more about polyprotic acids, but then we're going to get into pH and buffers. Like I said, next week's lab is going to be on pH, but realize that when we deal with pH, there's lots of calculations. So be ready on Tuesday. We'll be doing some calculations. Okay. Have a wonderful weekend, guys. See you on Tuesday.